Okay, so here's a quick review of the continuous time Fourier transform, something we've done we started in the last lecture. And just to give you a quick review, we said just like continuous time Fourier series, that analysis tells us that any periodic signal can be written down as a composition of complex periodic exponentials of frequencies, at different frequencies, with the caveat that the frequencies are harmonically related. So the frequencies take on values from a discrete set, right? So if omega naught, 2 omega naught, 3 omega naught, and so on and so forth, right? Integer multiples of omega naught. Uh, and then we extended this analysis to aperiodic signals, and we generalized it and then said that according to this Fourier analysis, any aperiodic signal can also be represented as a superposition of complex periodic exponentials, except that the frequencies that these exponentials take on values over a continuum of values. So it takes on a continuum of values over the real set, right? So from minus infinity to plus infinity, right? And why does that occur? We went about that analysis. We did that derivation to come to that conclusion, right? So just a quick recap. I mean, what was the result that we actually derived? That was that the aperiodic signal x of t can be represented as a linear superposition of complex exponentials of the following form, right? So this is x of t equals 1 upon 2 pi integral from minus infinity to plus infinity, x of j omega times e raised to power j omega t times d omega. And this is analogous to, if you recall, the synthesis expression that we had for the case of a continuous time Fourier series, right? Um, and it's x of j omega. I mean, what does x of j omega represent? I mean, what is x of j omega? I mean, this is something which is analogous to the Fourier series coefficients, right? So a sub k's, except that we're replacing the summation with an integral, and then replacing that ak with some form of x of j omega divided by 2 pi, and there's a d omega there as well. So what does x of j omega, I mean, what is x of j omega? Anyone? Right, so contribution towards the signal. Daniel, what kind of contribution do you mean? Of different frequencies. Okay, so x of j omega, as Daniel suggests, represents the contribution uh, of the frequency omega inside x of t, right? So x of t is made up of different complex exponentials of different frequencies, right? Or omega wali jo frequency ka contribution hai, x of j omega is that value, right? And this is complex. So this has an amplitude, this has a phase, right? And you evaluate this function for all omega going from minus infinity to plus infinity. And x of j omega is defined as, which is called the Fourier transform, is defined as the integral from minus infinity to plus infinity, x of t times e raised to power minus j omega t times dt, right? And we say that this is the Fourier transform. So this x of j omega is called the Fourier transform of x of t, and this is an equivalent representation of the time domain x of t in the frequency domain, right? So it's an equivalent representation. There's a one-on-one mapping on there, right? And this is called the inverse Fourier transform. And in the sense, because it's one-on-one, so if you're given x of j omega, which is an alternate representation, and if you were to convert it back to the time domain, I would say we take the inverse Fourier transform. So this is the inverse Fourier transform. Okay. So any questions about, so this is something we did last time. Any questions about this before I talk about some examples? So I've started posting some material on LMS as well, in which I try to relate this to practice. I mean, what does Fourier analysis in the practical world mean? So I'm going to put up some audio signals and compute the Fourier transform and just try to relate it to what you perceive the audio signals to be with the Fourier transform. So that should be up hopefully by tonight, inshallah. And any questions about this before I move ahead? All right. So then we did some examples, actually one particular example, and we said, this is x of t equals e raised to power minus a times absolute of t. We computed the Fourier transform this Fourier transform turned out to be 2a upon a squared plus omega squared. So this particular expression here, and then we try to build some intuition. I mean, what happens when a changes? And we said, Kitty, when a is small, the signal is relatively smooth, and in the frequency domain, most of the energy is concentrated at the lower frequencies. Um, um, as opposed to when A is large, that's when the signal suddenly decays and is not as smooth, right? It's not as smooth. And if I analyze it in the frequency domain, so this particular case that you see here, you see that the frequencies are now no longer only concentrated at the lower frequencies, but also at the higher frequencies. There seems to be a contribution of the high frequencies as well. So higher frequencies really correspond to the sharpness or the transitions कि कितना जल्दी signal change करता है, right? So that's sort of an intuition behind what x of j omega represent, and try to say this in this notes here as well. You're welcome to read this after the class, right? Let me do some other examples, continue this discussion with some more examples. And this example the next example I have for you is the following. Let's say I give you a signal which is x of t equals delta of t, right? The unit impulse. And I ask you to find what the Fourier transform for this unit impulse is, right? So what do? How do I compute the Fourier transform, right? So I need to compute the Fourier transform to be able to find out, okay, what type of frequencies does this unit impulse contain. I just apply the definition, and I know that x of j omega by definition is equal to integral from minus infinity to plus infinity. What do I integrate? I integrate x of t times e raised by minus j omega t dt, right? So this is the definition, and I just plug in what x of t is, which is delta, right? So this is delta, and this is e raised to power minus j omega t times dt, right? What does this turn out to be equal to? So what is this equal to? Anyone? I mean, what does this integral evaluate to?
1.
1, right? So this is 1, and this goes back to बहुत सारी चीजें पहले की थी, right? So you just, this is sampling property of the delta function. You just plug in t equals 0 there, and you get 1, right? So for x of j omega, therefore, I mean, the conclusion is equal to 1, right? It stays flat. What does this mean really then? That means that what are the contributions inside the delta of t as far as the frequency is concerned? All frequencies from minus infinity all the way up to plus infinity contribute equally to make up this unit impulse function, right? So if I were to say कि इसकी, I mean, frequency contribution किस band में limited है, I'd say कि यार this is not limited to a particular duration of the frequencies. It is rather from minus infinity all the way up to plus infinity. It takes up infinitely a frequency duration of which is infinitely long to make up this delta signal, right? This delta of t, and one of the intuitive explanations of why that is so is because delta, if you really think about this, delta of t is something which is extremely sharp as far as transitions are concerned, right? So it stays zero, and then it goes up, right? And it goes down in an infinitesimally small duration of time, right? So the rate of change, if you will, of this delta function around this t is infinitely high, right? And that's, I mean, one of the intuitive explanations of behind why you need so many high frequencies to make up the delta signal. Okay, so this is an important result, that if this theoretical construct that we have, which is the unit impulse, the Fourier transform for that is just flat. Okay, so this is one example, and then we're going to use this a little while later as well. Okay. Any questions about this? Okay, जी उमर.
सर अगर हमें कोई सिंगल डाटा पॉइंट हो मतलब हमारे ग्राफ में,
Yeah.
तो क्या उसको हम इम्पल्स से रिलेट कर सकते हैं? मतलब एक इम्पल्स एक सिंगल डाटा पॉइंट होता है.
Right. So you see the single data point as far as continuous time signals are concerned, I mean, that is different than a delta function. How so? Can you, Umar? So
Yes, sir.
I claim a single data point is
Yes, sir.
different than a unit impulse. How is that?
सर उसकी I'm not sure.
Right.
Maybe
So
उसकी properties वगैरह डिफर करती हैं.
you see,
The impulse is defined to be zero otherwise.
yeah, and then there's another important property of the unit impulse.
Area
उसकी height क्या
one, area one होता है.
area 1 होता है.
Area one होता है. हाँ, तो लेकिन data point का नहीं होता.
Data point is infinitely high, right? As the height is infinitely high, right? Infinitely large as far as the delta of t is concerned, right? So that the area is equal to 1, as opposed to what you're saying is कि यार, let's say there's something that we say कि जी time t equals 0 पे वो value 1 लेता है.
Yes, sir.
ठीक है, इसका एरिया अंडर द कर्व निकालें तो क्या आएगा? वो 0 आएगा.
0 आएगा.
Right? So that is not the same as the delta function, right?
तो उसके Laplace transform हम ये Fourier transforms की हम कर सकते हैं?
नहीं, so Fourier transform उसका 0 है, because that singularity at time t equals 0, it does not really matter. I mean to say so small के उसके अंदर area कुछ है ही नहीं, तो वो it's as if it was not there, right? Now what you may be referring to from practice is where you have sample data. आप कहते हैं कि जी मैं डेटा ये है और मैं उसको हर 1 सेकंड पे सैंपल करता हूँ और किसी एक पर्टिकुलर सैंपल पे उसकी वैल्यू ये है और बाकी सारे सैंपल्स पे 0 है.
Yes, sir.
That may have been what drove this question in the first place. That is a different case, and that is not the continuous time signal. That's something called a discrete time signal, which we're going to do after we're done with this Fourier transform.
Okay, sir. Okay. Thank you.
Right? Masna, आपने अपना हाथ खड़ा किया था. Did you have a question or did you want to answer?
No, sir, I had the answer.
अच्छा, आपका क्या आंसर था?
Sir, यही कि एक पॉइंट का डेल्टा पॉइंट has an infinite height, लेकिन जो पॉइंट होता है उसकी finite height होती है.
Good. Right.
So
exactly.
the area is different.
Exactly. Good. Right. So that's that. Right. So the next example is let's consider a signal x of t, which is equal to, right, so let me pull this up, is equal to 1 for all values of t which satisfy capital small t is less than capital T, t1, and is 0 otherwise. Right? So if I were to sketch this out, what does the signal look like as a function of time? So if this is time t, and if this is, I'm trying to plot x of t, what does this signal look like? जी अब्दुल्ला.
So t1 और minus t1 के दरमियान में horizontal line होगी और बाकी जगहों पे 0 होगा.
Right? So this is square. Good. Right? So we say this is square pulse. It's not periodic, by the way. Right? So it just stays 0 for all time from minus infinity all the way up to minus t1, and then it stays 1 for this duration, which is 2 times t1, and then it goes back to 0 again. Right? And the height here is 1. Right? So this is that signal. Okay. And then I ask you to determine what the Fourier transform for this is. Right. Gizan.
सर शॉर्ट क्वेरी से सही जो ये वाला ग्राफ है, दिस इज डिफरेंट फ्रॉम एनी जो हमने पहले ड्रॉ किया था, वो भी सेम ही था ना? लाइक व्हेन वी टेक t mod is less than t1 and then 0 से t1 is greater than mod t and less than t by 2, सर वो भी सेम चीज ही होती है ना, लाइक
No, that
बस
was a
एक्सेस.
that was a periodic signal, right? So this is not a periodic signal anymore.
Okay, हाँ, okay sir, I got it.
It stays zero outside T1 से
Yes sir,
बाहर सारा zero
yes
रहता है. Okay.
जी sir, I got it. Sorry sir.
So now you're required to find the Fourier transform. How do I do it? Just apply the definition, right? So x of j omega, the transform is defined as integral from minus infinity to plus infinity, x of t e raised to power minus j omega t times dt, and this is therefore minus t1 to plus t1 integral of e raised to power minus j omega t times dt. Right? Why do I do this, by the way? I mean, why this? Because the signal itself is equal to 1 only between minus t1 and plus t1 and 0 outside. So I just change the limit. That only changes the limits as far as the integral is concerned, right? And if I evaluate this integral, this turns out to be equal to e raised to power minus j omega t divided by minus j omega, and this is minus t1 to plus t1, right? What does this reduce to? This is e raised to power j omega t1 minus e raised to power minus j omega t1 divided by j omega. So I have skipped a step. I've just incorporated the minus sign inside the numerator. जो नीचे वाला minus sign है denominator में, I've incorporated that into the numerator, right? Can you simplify this a little further? This appears to be complex. I mean, but I claim this is actually not complex. When I say complex, I do not really mean difficult or sophisticated. When I say complex, I say this is a complex signal, appears to be a complex signal. But in fact, it is not. What is this equal to? Ji Ibrahim.
Sir, I think it is something वो जो साइन की हमने आइडेंटिटी पढ़ी थी यूलर्स वाली, उससे
Good.
रिलेटेड कुछ.
Excellent.
2 से मल्टीप्लाई डिवाइड करके कुछ को बना सकते हैं सर.
Excellent, right? So as Ibrahim suggests, let me multiply with 2 and let me divide by 2, right? And then what I really get is a sign here, right? So it turns out that this is equal to sine omega t1 divided by omega, right? So this is, I mean, what's really gone on is, actually there's a 2 there as well.
So 2 आएगा. So 2 आएगा. Yeah.
Excellent. Thank you, Zan. So असल में क्या हुआ? I mean, this thing here, which I am circling inside the, sorry, this thing here, this is actually sine omega t1. That's all I've done. All right. So our conclusion is as that square pulse that you have in the time domain, if I compute the Fourier transform for that, the Fourier transform turns out to be equal to this nice looking, I mean, to me it looks nice, form which is real, is not a complex signal. Right. Okay. First off, it's real, right? So if I were to sketch this, I only need to sketch the real part, okay? What would the sketch look like? What would the sketch look like? So if this is omega, right?
सर
जी.
0 पे इम्पल्स कितना कुछ होगा?
All right. क्यों?
-0 सेकंड के डिनोमिनेटर में
डिनोमिनेटर में 0 रहा है, पर न्यूमरेटर में भी 0 रहा है.
तो सर वो 0/0 पे L'Hopital लगाएंगे या फिर like?
Yeah, you could apply L'Hopital's if you want, right? You could do that and go ahead and do it. But there's a much easier way of finding out what this should be at omega equals 0, which is just simply I go back and see yaar ye kya tha integral. Right? If I just plug in omega equals 0, right?
T होगा फिर
Omega equals 0. This is just 0. So e raised by 0, and that's just 1. So the integral is going to turn out to be equal to 2 times t1.
Yes, sir.
Right? So the height is not 2, but rather 2 times t1, right? And as the frequency increases, as Tala suggests, the height decreases, but then it's a sinusoid as well. So there's going to be some sort of oscillation, and those oscillations are going to, the magnitude of those oscillations is going to decrease with time as omega, decrease with omega as omega increases. Okay? So it's a linear sort of a decaying sign, as Daniel suggests as well. Okay, so I'll go ahead and sketch this out. This is what the Fourier transform looks like, right? So as we found out, the height here is 2 times t1, which you could, by the way, just apply L'Hopital's and find out. Okay, this indeed, it turns out to be equal to 2 times t1. My question is, okay, what would this point be? I mean, what is the point on the frequency axis, the first point on the frequency axis for which there is a 0 crossing? When does this curve cross the 0 axis? For what value of omega is this equal to 0? And ye value kya hai? That's my question. Anyone? Okay, Ibrahim says 2 pi time divided by t1. Excellent, Ibrahim. There's a slight bit of a problem with that 2 pi, right? So sine, yeah, I think what you're doing at the back of your head is you're saying that sine 360 degrees is 0 or sine 2 pi is 0, right? But sine pi is also 0, remember. Right?
So pi by t will work, I guess.
Pi by t1, right? Excellent, right? So this would be this 0 crossing would be pi by t1. And similarly, this 0 crossing would be at minus pi by t1. What about this 0 crossing? The second 0 crossing?
So 2 pi by t1.
2 pi by t1, right? By t1 and so on and so forth, right? This is 3 pi by t1 and so on and so forth, right? So the 0 crossings are actually spaced pi by t1 radians per second apart. Okay? Right. So let me sketch this out just to try to get some intuition here. What happens if I increase t1? What happens if I decrease t1, right? So what we've been able to conclude is the following, that if I give you a time domain signal, in which this is the t-axis, Daniel, go ahead.
सर ये आपने 2t1 कैसे लाए मुझे जरा दोबारा बता दें प्लीज.
Okay, so one of the ways you could do this, obtain this 2t1 is just apply L'Hopital's on x of j omega, right? So you apply L'Hopital's rule to determine x of j times 0, right? And you will find that this indeed turns out to be equal to 2 times t1, right? I mean, you take the derivative on the numerator, and then of course 2 times omega t1, and you just then plug in omega equals 0. Okay? So 2 times t1. Okay? And you get that. The other way, Daniel, is to just look at this thing here, right? Because this is x of j omega, right? If this is x of j omega, what would be x of 0? I just plug in omega equals 0 here, right? And if I plug in x omega equals 0, e raised by j omega t becomes 1, and you're integrating 1 from minus t1 to plus t1, that's just 2t1. And for me, that's a much easier way of finding out what the value should be at omega equals 0. Okay, Daniel?
जी सर, आगे समझ. Okay.
Zen, go ahead.
सर वो L'Hopital से भी like confirm है ना कि वो 2t1 ही आएगा, like मतलब के
जी 200% confirm है.
जी सर, thank you.
Right. Yes, Talha, the derivative will be respect to omega because limit जो है omega की डाल रहे हैं, right? Okay. Now, so what I was doing was, let's look at the time domain signal. So let me pull this down a little bit. Right. So this is a time domain signal. And this time domain signal looks like the following. It's a square wave. This is T1 and this is minus T1 and the height is 1. And if I compute the Fourier transform for this, right? So this is a notation that I used in the last lecture as well. Just says its equivalent representation in the frequency domain is the Fourier transform, right? And that Fourier transform, as we did the sketch just above, is that decaying sine, if you will, and it's actually called the sync pulse, right? So the name for that is a sync pulse. So this is x of j omega. And what it looks like is a linearly decaying sinusoid, where the first crossing occurs at pi by t1, and over here this is minus pi by t1, so that this this length here, this of the main lobe, is equal to 2 pi by t1. All right. Now, what happens if I increase t1, or what happens as I decrease t1? Gzen.
सर अगर आप T1 बढ़ाएंगे तो जो y एक्सिस का एम्पलीट्यूड है वो बढ़ जाएगा और जो x एक्सिस के ऊपर जो वेव्स हैं वो पास आ जाएंगे
right,
वो वेव आ जाएंगे फ्रीक्वेंसी जो
right. So if I expand Abdullah, so my question abhi maine kya pucha, if I increase t1, right? That's what I asked, right? Right. Okay, good. Right. So my question now, first FSKG, as t1 increases, the width of the main lobe, which is 2 pi by t1, that decreases. So that's compressed, right? So the frequencies are therefore, the frequency contributions are therefore concentrated more in the low frequency regime than they are at the high frequency regime, right? So frequency domain में compression हो रही है जब time domain में expansion होती है, right? Does that make sense or not? And as vice versa, as vice versa, what happens as T1 decreases, right? As T1 decreases, 2 pi by T1 increases, or the width in the frequency domain increases, right? So it's there's appears to be a counter effect. I mean, which in the sense that expansion in the frequency domain or expansion in the time domain results in a compression in the frequency domain, right? So expansion in the time domain results in a compression in the frequency domain and vice versa, right? Right. So F and T have inverse relationship, right? As Zen says as well. So why does it make sense then?
So because the formula says so, because
I mean, formula to आपको चीज बता रही है, लेकिन I mean, sense when you're trying to make sense of something, right? So there has to be some external guiding principles of why it makes sense, because it has to conform to some other thing that another way of thinking,
yes.
Right? Another way of thinking should be some intuition that you're thinking about this about, right? So as you decrease T1, right? So as you decrease T1, I would say that the signal makes sharp transitions, right? क्योंकि T1 अगर छोटा करता जाऊंगा, right? The transition per unit time increases, right? And that's sort of saying that the frequency content increases, right? As opposed to if I increase T1, right? The signal becomes smoother and smoother. And the transitions per unit time actually decrease, and therefore the frequency content also decreases, right? So that makes sort of sense here, right? Okay.
So can you elaborate more upon transitions per unit time, like transition
ट्रांजिशन
from
इससे
what to?
कितना स्मूथ है, कितना 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 स्मूथ है और कितनी वेरिएशन ऑफ सिग्नल के अंदर, राइट? सो आई लेट मी से दैट वे, राइट? सो व्हाट इज द अमाउंट ऑफ वेरिएशन इन द सिग्नल, right? Now we said
Yes,
that delta has an infinite amount of variation because it just goes what, right? It goes boom up to infinity and boom down to zero in an infinitesimally small duration, in a very, very small duration, right? And that means
yes, sir.
it's the variation in that signal is extremely high, and that's why it took up infinite uh, amounts of frequencies, right, from minus infinity all the way up to plus infinity to make up that delta signal. Okay, now
Yes, sir.
it's the same sort of idea as you could use for this x of t, this is squared pulse here as well, right? Okay, if I increase t1, right, it's sort of smooth. It makes a transition and then stays smooth for a long duration of time, and then after a long duration of time, then it makes another transition and then stays smooth as well once again, right? As opposed to if t1 is small, it stays smooth and then makes a transition and then stays smooth for a very small duration of time and then makes a transition again. And I could say the variation in that signal is slightly higher, or it's not slightly, is higher. And that's why it would need higher amounts of amplitudes for the higher frequencies to make up the signal. And that's sort of an intuitive take on what's really happening. Okay. I saw somebody else raise their hand as well. I mean, did you have a question? I forget किसने कहा गया था. जी दानियाल.
सर मेरा था, मैं उसमें ये कह रहा था कि T1 इसको हम इस तरह भी देख सकते हैं कि वो साइन की आर्गुमेंट में ओमेगा T1 है ना, तो T1 एक्चुअली फ्रीक्वेंसी को रिप्रेजेंट कर रहा है, जैसे हम ओमेगा नॉट T देखते थे टाइम डोमेन के अंदर.
Yeah, sort of. Agreed. But and that's an inverse relationship.
जी.
ठीक है. Danial, so Umar, you had a question.
सर लेकिन जो हमारा ये स्टेप अप है और स्टेप डाउन है, ये तो फिर भी इन्फिनिटली स्मॉल टाइम में ही हो रहा है.
बिल्कुल.
मतलब सिग्नल की वैल्यू चेंज हो रही है
Excellent.
विदाउट एनी डिले.
Excellent point, Umar. Right? और उसकी वजह से क्या है? उसकी वजह से it still takes up frequencies all the way from minus infinity to plus infinity to make this signal, right? I mean, this signal never ends. This frequency domain signal never ends. It keeps on going and going and going and going. Okay? So if I were to say, yaar, quick S, is this a band limited signal? When I say a band limited signal in the sense, I'd say the Fourier transform is only limited between minus B and plus B. Does a B exist like that? No, but it doesn't exist. It goes on and on and on, right? And that's actually because of this discontinuity, because of this transition, that you have infinitely many frequencies that make it up, or a frequency band of infinite length, which is required to make up this square pulse. Okay? As opposed to something I'm going to do next. दानियाल, आपका क्वेश्चन अभी भी है?
जी सर मुझे इन दोनों ग्राफ्स को आपस में रिलेट करना नहीं आ रहा है. मतलब जो राइट वाला ग्राफ है ये मतलब टाइम इस पे स्टॉप हुआ है ना एक.
नहीं टाइम स्टॉप नहीं हुआ.
इसकी तो अच्छा
राइट. सो you take the signal all the way from minus infinity to plus infinity. So पूरा का पूरा signal आ गया. Right? And then you transform it into another domain. And that's why it's called a transform. It's a transformation from the variable t to another variable, which is omega now. It's an alternate representation. Right?
Okay.
And the interpretation is just like the Laplace transform. You've done Laplace transform, right? Where you transform the time domain into the S domain, which is a Laplace domain. And they're equivalent representations, which goes back and forth. Okay? So you're not stopped at a particular time t, right? You take up the entire signal from minus infinity to plus infinity and done an operation on it. And after you do that operation on it, then you transform it into another domain, which is the omega domain. Or relationship uski kya hai? It is that through superposition of complex exponential. right? Which is that Fourier transform, inverse Fourier transform relationship. Okay. So Ibrahim, we can have a discussion on this offline as well, right? Right. I want to come to this next example, which is sort of related to the excellent point that Umar raised, which was KG is still a transition, right? Still a transition, right? So let's look at another signal and say, KG, let x of t be some signal, which is a time domain signal. The Fourier transform of which is given. That's given by x of j omega is equal to 1 for all values of omega which are less than b, absolute values less than b, and is 0 otherwise. Okay, so what does x of j omega look like? X of j omega, क्या दिखेगा x of j omega, right? So if this is omega, it's a, as Daniel says, it's a square pulse, but in the frequency domain, right? So this is what it looks like. ये है, ये है, ये है, ये है. And this is, so this is B. And what about the other side? This other side is minus B, right? So it's a length, it's a square pulse in the frequency domain, which is of length 2B, right? What you're required to do is determine x of t. Now, as far as this x of j omega is concerned, I mean, compared to all of the other signals that we've taken or we've considered, the Fourier transform for this signal is only limited between minus b radians per second and plus b radians per second, right? In between that. And outside of this interval, the Fourier transform is 0. What that means is that the signal that we're about to find out is made up of frequencies which are only between minus b radians per second and plus b radians per second. And outside of this, these are all zeros. The frequencies are all zeros. Okay. So what is that signal? What would that signal be? How do I find the signal, by the way? क्या करूं मैं? If I'm given the Fourier transform and I am required to find the time domain signal which corresponds to this Fourier transform that I'm given, what do? You use the inverse Fourier transform integral, or the relationship that you're given, right? So the solution is the following. X of t, by definition, I know, is equal to 1 upon 2 pi integral from minus infinity to plus infinity x of j omega e raised to power plus j omega t times d omega, right? So this is the definition of the inverse Fourier transform. And what does this reduce to? This reduces to 1 upon 2 pi. This integral goes from minus b to plus b, and this is e raised to power j omega t times d omega. Okay. What is this equal to? This is equal to 1 upon 2 pi, and I have j omega in the denominator, and this is e raised to power j omega t evaluated b and minus b. So this is 1 upon 2 pi. This is e raised to power j b times t minus e raised to power minus j b times t divided by j sorry, j omega to nahi aana chahiye. So this is jt, sorry, because you're integrating with sec omega. Okay. Yeah, what is this equal to? Another sine, right? And this time around, I'm not going to go into those details. So this is sine b
over 2t.
times t divided by, there's so 2 sine के अंदर आ जाएगा, right? And this would just be pi t. Okay.
Excuse me, sir, शुरू में आपने कहा था कि like you said something about the frequency of the original signal just by looking at the graph के, सर वो दफा दोबारा repeat करते हैं. You said के
Looking at the
you
graph.
said something के sir, yes sir, you said के जहाँ पे 0 हो रहा है तो like sir you said something about the frequency of the original signal just by looking at the transform वाला graph.
Okay, so when we say what is the frequency of the original signal, that by itself holds no meaning. Why? Because when you say what is the frequency of the signal, you या तो periodic signal ना तो फिर तो ठीक है, right? But we're not talking about aperiodic signal, right? So there's not just one frequency that makes up the aperiodic signal, but a bunch of perhaps infinitely many frequencies that combine together in a very, very specific fashion by proper weighting and phase values, so that when they add up, you get the time domain signal that you're looking for.
Yes, sir.
Okay. And x of j omega tells you, okay, what kind of weightings do you need to do for each one of the frequency components. Right? ये question था या कोई और question कुछ और था?
वैसे ये था.
Right. So I just explained what Fourier transform is essentially.
Yes, sir. Yes.
Okay. All right. So this x of t is sine bt upon pi t. Can we sketch this out in the time domain? Right. So let's say this is times t, and I want to sketch out what x of t is as a function of time. What would it look like? Right. So
sir, what is like the sign जो हमने ऊपर बनाया था उसी तरह से नहीं होगा?
Exactly उसी तरह की चीज होगी, right? Except that there's no 2 there, right? And there's another pi here, right? So it's still a sine, which is sort of a proportional sink, right? Which decays linearly. The amplitude of which decays linearly. And what is this signal at x of 0? I'll leave this as an exercise, right? You just apply the L'Hopital's rule if you wish, or you plug in t equals 0 here to find out what this integral is, और यहाँ पे फौरन पता चलेगा. कोई बता सकता है मुझे क्या वैल्यू होगी? B by pi. Excellent, Daniel. Awesome. Right. So there are people messaging me on Slack right now. They don't know I'm in a class. So this is recorded. So जिसने भी message किया he'll know के pointed. All right. So this is B by pi, as Daniel correctly suggests. Okay. And this corresponds to the Fourier transform of, and that Fourier transform is just a square pulse, if you will. And this is x of j omega. And this is b, and this is, or sorry, this is not t. This is omega. And this is minus b. Oops. It's minus b. And the height is 1. Right? So, I mean, what are some of the intuitions that we can derive from this? I mean, you can, once again, see what happens when you do the compression in the frequency domain, and or vice versa, what happens, and you'll once again find out that expanding in the time domain would result in a compression in the frequency domain and vice versa. Okay, and just I mean, what would this first zero crossing be equal to? Who's going to tell me that? If somebody is not spoken yet, please go ahead so I can mark your CP. Preferably not on the chat window. Chat window automatically record here. Right? When would this first zero crossing? Where would this first zero crossing be? Right. So this would be when B times T equals pi, and therefore T equals pi divided by P. Excellent. Right. This is pi divided by B. And similarly, this is minus pi divided by B, and so on and so forth. Okay. And you can once again find out, okay, as I do the compression in the time domain, I'll get an expansion in the frequency domain and vice versa. Right. But what this also corresponds to, so there is, so Daniel says, why is there some duality between these transforms? Yes, there is duality between the transforms. Daniel, can you guess why? You raise an excellent point. क्या ख्याल है किस वजह से? Even though we're not going to explicitly discuss this property here, लेकिन why do you think this is so? Why is this the duality here?
सर टाइम और फ्रीक्वेंसी का कोई रिलेशन है शायद.
Okay, time frequency का relationship. All right. किस किस्म का relationship? Ibrahim, you want to say something?
जी सर, मैं कह रहा था कि हमारा जो फोरियर ट्रांसफॉर्म है और इनवर्स ट्रांसफॉर्म है वो सिमिलर सॉर्ट ऑफ इंटीग्रल्स हैं, और उसमें हम e raised to power minus j omega t से मल्टीप्लाई करके तो सिमिलर वो है एक्सप्रेशन.
Excellent, right? And the duality is there because if you look at the Fourier transform and the inverse Fourier transform relationships, they're very, very similar, right? In one of them, there's a plus j omega t, the other one is minus j omega t. E is by minus j omega t, was एक और में is plus j omega t, and that's the difference. And one of them has a 1/2 pi, the other one does not, right? So there's a strong duality between the two, right? So that's an excellent observation. Okay. Now, one thing I do want to say here is that this particular signal, I can say that this is a band limited signal, right? We say that this signal is a band limited signal. What do you mean by that? Ibrahim, did you have a question?
नहीं सर, वो पहले गई था.
So way that the signal is a band limited signal. What do I mean by the fact that this is a band limited signal?
सर सिर्फ लिमिटेड फ्रीक्वेंसीज कंट्रीब्यूट करती हैं इसके लिए.
Right, it's a limited frequency. The frequency content is only limited between minus b and plus b radians per second, right? And outside of this band, it's always zero, right? So that's why it's called a band limited signal.
Excuse me, sir.
जी जान.
सर हम ये इम्प्लाई कर सकते हैं कि जो उसका फोरियर ट्रांसफॉर्म है, जैसे वो एक b और माइनस b के दरमियान लिमिट हुआ है,
Yeah.
तो इसलिए उसको बैंड लिमिटेड बोल रहे हैं.
Excellent. Exactly why. So since the Fourier transform is non-zero only when omega is less than b, right? And outside of this interval, this has zero, and as Salah also suggests, excellent Salah, is contribution from limited frequency, right? Limited, when you say limited frequency, is a limited band, right? So there are infinity many frequencies inside the band here, by the way, because it's a continuum of values. Okay? But what you observe is that time domain में signal क्या है? Time domain में that signal is infinitely long. The time domain. Okay. All right. Let's do I have another example? All right. Are there questions here about these examples that we've done before I move? Okay. So one thing I do want to say, I think I forgot to mention this earlier, and I don't want to spend too much time here, which is convergence of the Fourier transform. Very, very briefly. And we just look at x of j omega, which is equal to integral from minus infinity to plus infinity, x of t times e raised to the minus j omega t dt. And since this is an infinity long integral, right? So this integration is taking place over a time duration which is infinitely long. And whenever you're dealing with things which are infinitely long, right, whenever you're integrating from minus infinity to plus infinity, you may run into convergence problems, right? This integral sometimes may not converge, right? And it turns out that there's a theory behind it. So when will this converge? When will this not converge? Right? And I don't want to go into a lot of details there. It turned out that there's some conditions called Dirichlet conditions, similar to the conditions that you would have read hopefully in the Fourier series analysis as well. Right? All I want to say is that as far as we're concerned, so important point जो हम सिर्फ देखेंगे, and we're just glancing over this without the proof, is that x of j omega converges. When I say converges, what does that mean? That means that
finite
the
value finite value आ जाती है, like
finite value, the absolute value of x of j omega is less than infinity. That's what it means for all values of omega, no matter what omega is. It stays, it's bounded, right? It converges. It converges if x of t is absolutely integrable, right? The integral of the absolute value from minus infinity to plus infinity dt is less than infinity. Okay, so I just state this here. I am not going to do this, the proof for this. Okay.
So can you give an example? कौन सी converge नहीं होती, like just an example of a graph
right.
or
So
something?
all of the examples that we've seen right here are absolutely integrable, right? And to consider the case where is not absolutely integrable, let's consider this first example: x of t equals a raised to power minus a times absolute of t, right? For what values of a will this signal not be absolutely integrable? Greater than, less than 0. Excellent, right? If a is negative, e raised to power minus a times absolute t would actually be a growing exponential. And if it's a growing exponential, it will not be absolutely integrable. Now, for that, you go ahead and apply the same transformation that we did in the last class. You will find that this is not equal to what is written here. Why would that be? The reason why that would be because यहाँ पे जब भी infinity आएगा ना, ये वाला infinity, right? This thing here evaluated at infinity will not converge. It will actually go to infinity, and that will create convergence problems, right? Will not be converged, right? And that's one of the examples. Okay, and there could be many others. Right. Now, with that note, I will start a new section, which is, can we compute the Fourier transform of periodic signals? Okay. Now, this may run counter to what I just said. How so? So now we're dedicating an entire section to computing the Fourier transform of periodic signals. And I claim that this runs counter to the statement I just made earlier, which said that the Fourier transform converges only if the time domain signal is absolutely integrable, right? So why does it run counter to the statement that I made? क्या ख्याल? I mean, would somebody else like to speak up? My question is, we want to talk about computing Fourier transforms of periodic signals, right? And I say, yaar, this appears to be in contradiction to the statement that I just made, which is the Fourier transform converges when the signal is absolutely integrable. Why do I say that? Can you make that connection? I mean, there's something contradictory there. क्या ख्याल है मुस्तफा? जी दानियाल।
सर पीरियोडिक सिग्नल्स जो होते हैं वो तो इंटीग्रेबल नहीं होते ना, मतलब उसकी इनफिनिट होती है।
Excellent. So Daniel correctly points out that periodic signals are not absolutely integrable. Right? Periodic signals are not absolutely integrable. If periodic signals are not absolutely integrable, based on the statement that we just made earlier, the Fourier transforms for periodic signals will not converge. Yet I am going to dedicate a section on trying to compute the Fourier transform of periodic signals. Right? So it turns out that we even though the periodic signals are not absolutely integrable, we will find a way of some sort of representation which would allow us to represent the Fourier transform for periodic signal, and things have kind of become clearer as we move along. Okay. Before I move, I just want to say about the CPE. So here's how I compute the class participation. Right. So the people who join the class, and then there are people who type, and then there are people who speak up. The most points are reserved for people who speak up, and there are points for those who type as well, even if it's yes, no, or something. Okay. So और कुछ नहीं कर सकते, तो just type something. I just do a check mark. So for people who speak, I don't care कि वो unnecessarily. Okay. Zen, are you pointing to yourself? Yeah. I'm just kidding, by the way. जी Zen. Can we talk?
नहीं सर सर लाइक मोस्टली वो मुझे थोड़ी बातें समझ नहीं आती हैं, फिर जब मैं वो पूछता हूँ तो फिर मुझे लगता है कि वो बाकियों को समझ आई होंगी, मैं डांबू तो वो फिर ऐसे ना हो।
No, never do that. Okay.
ओके सर,
Right.
इसलिए
So
मैंने कहा कि
if you speak up, regardless of what the question is, I will provide you with points, but regardless के points हैं या नहीं है, I mean, there should be nothing stopping you from asking those questions. Okay.
Yes, sir.
Never underestimate yourself. Never doubt yourself.
Yes, sir.
Right. So Abdullah, why ironic? Right. Zan sabotaging. अब सब बहुत सारे मैसेज आना शुरू हो गए हैं. Right. Okay. और कुछ नहीं तो इसी पे कुछ कमेंट कर दें यार, so I can mark your CP. Right. अच्छा जी. So we're talking about Fourier transform periodic signals. And the first question is, why would we want to talk about Fourier transform periodic signals? Did not we just say that Fourier series applies to periodic signals and Fourier transform applies to aperiodic signals? Right? So Umar, you raised your hand.
सर मैं वो यही पॉइंट पूछने लगा था कि हम पीरियोडिक सिग्नल्स तो फोरियर सीरीज में करते थे, फिर जब एपीरियोडिक आया था तो हमने फोरियर ट्रांसफॉर्म इंट्रोड्यूस करवा दिया था.
Right.
तो अब फोरियर ट्रांसफॉर्म में पीरियोडिक क्यों ले आए हैं?
Right. Excellent. Right. Zabardast. And that's a very valid question, a very valid reservation. Right. That each and every one of you should have had. Right. And the answer to this is that we want to come up with a generalized framework, so that generalized framework applies to any signal regardless of whether it is periodic or aperiodic. I don't want to say yaar ye series hai, ye transform hai. Can I just generalize a transform so that this transform is now applicable not only to aperiodic signals but also to periodic signals, and that generalization will help in some applications that we're going to see a little bit later. Okay. So that's the motivation behind why we want to talk about Fourier transform for periodic signals. We want to generalize it. Okay. Now, what is the most fundamental or the basic signal or naivest of signals, which is a periodic signal? And that we found out is the complex exponential. Right? Periodic complex exponential, right? Which is a period of 2 pi by t. Or 2 pi by omega naught, right? That's a fundamental. Okay. And this is, of course, not absolutely integrable. How do I compute the Fourier transform for this? how do I compute the Fourier transform for this? Right, and I just apply the definition, and that definition is that this is e raised to power j omega naught t times e raised to power minus j omega t times dt, an integral from minus infinity to plus infinity. This is integral from minus infinity to plus infinity, e raised to power j omega naught minus omega times t times dt. And I need to compute this integral. It turns out this integral is, my screen is stuck, is it? All right. All right, Asisane, you can't hear? Can you hear now, Hamza? All right. So how do I compute this integral? So all I will say here is try computing this. You will run into problems. And the problem is with respect to, is going to be with respect to convergence, right? So it turns out that this integral will not converge always, right? And so I leave this off as an exercise, right? So this is much, much harder to do, okay? On the other hand, let me sort of, use results that people have derived already to do some sort of reverse engineering. Let's say I say that if x of j omega is equal to some 2 pi delta omega minus omega naught. Right? So Daniel, we cannot take only one period because the definition of the Fourier transform says you have to integrate from minus infinity to plus infinity and not over one period. That's the problem. Okay. So if x of j omega is 2 pi delta omega minus omega naught, the question is, what is x of t? Right? So now we're talking about a Fourier transform which takes on this this delta looking expression, right? So with this is omega equals omega naught pi. There's an impulse of height 2 pi, right? What I mean by that is the area under that is equal to 2 pi, right? In order to determine what x of t is, I will just apply the definition of the inverse Fourier transform. X of t equals, right? Esan, unmute करें और बोलें.
सर x of t से start किया था वही होगा.
Okay, excellent. Why do you say that? Did you compute the integral or एकदम से इल्हाम हुआ कोई?
Sir, intuition, I guess.
Intuition, right? So this is your intuition is exactly right? So this is what I do, right? So this is e raised to power j omega t and your integral over omega. Okay? So this is just, I just apply the inverse Fourier transform relationship to this, and I see that this 2 pi cancels with this 2 pi, and what I'm left with is this integral from minus infinity to plus infinity, delta omega minus omega naught, e raised to power j omega t times d omega. And what is this equal to? This is indeed equal to e raised to power j omega naught t, and this comes about once again because of the sampling property of the unit impulse. Okay, because of the sampling property of the unit impulse, right? Right. So what is the conclusion? So we went about, and I sort of admit that the way we went about this is in a reverse direction, right? So let me assume कि यार ये है और उसका Fourier transform निकालते हैं and click, and it turns out to be exactly what we were looking for, right? So as far as we're concerned, let's just stick with this approach, right? For those of you who want to do it in an advanced fashion, why don't you just try to compute this integral and prove that this is actually equal to 2 pi times delta omega minus omega naught, right? But nevertheless, so our conclusion is the following. The conclusion is that if I take x of t, which is a periodic signal, e raised to pi j omega naught t, and I compute the Fourier transform for that, the Fourier transform for that turns out to be equal to x of j omega equals 2 pi delta omega minus omega naught. Okay, so this is the fundamental result that we're going to now use for all of the examples we do. Okay. Now the question is, KG, is this Fourier transform is it convergent or not convergent? So clearly, x of j omega is not bounded. It's not bounded, Daniel. Is not convergent. Because of what, Daniel? Why is this not convergent? The reason why it's not convergent is because the delta function is infinitely high, right? The height for that is infinity, right? So it's therefore this x of j omega is not bounded and it's not really convergent. Okay, it does not converge. However, and this plays nicely into the result that I mentioned just a while ago, which said the signal has to be absolutely integrable for the Fourier transform to converge. And we clearly found out that the signal is not absolutely integrable, and of course the Fourier transform turns out to be non-convergent as well. Yet we've actually intelligently used the impulse function to try to represent a divergent quantity, a non-convergent signal in the frequency domain, right? And this is going to come in handy later on as well, right? So for periodic signals used by j omega naught t, I can come up with a Fourier transform for that periodic signal in terms of the delta function, which stays 0 always, except at omega equals omega naught. Okay, so but we have used the impulse to represent this. Okay, and if I were to sketch this out, this x of j omega as a function of omega, what would this be? This must be a single impulse residing where omega equals omega naught, and the height for this is going to be 2 pi. Okay. Now, here's a question for you. So how will we be using this? ऐसा थोड़ी देर बाद अगले कुछ perhaps one lecture from now or 2 lectures from now, I'll tell you. Okay, let's just try to go through some exercises. So if I give you x of t equals cosine omega naught t, right? Cosine omega naught t, and I ask you to determine the Fourier transform for this. How do you determine the Fourier transform? Achha, by the way, before I go that route, right? So you see, I mean, there's a very clear intuition which follows here. When I say कि e by j omega naught t है, उसका Fourier transform क्या है? The Fourier transform for that is just an impulse, and that impulse resides where at omega equals omega naught. And that clearly indicates that the signal x of t equals x e raised by j omega naught t is indeed made up of complex exponentials. And that complex, there's only one complex exponential in there. And that complex exponential has a frequency, which has a frequency equal to omega equals omega naught. All of the other frequencies are zero, right? So it plays in very, very nicely into the interpretation of the Fourier transform that we made already, which was KG. Any signal can be represented as a superposition of complex exponentials of frequencies varying from minus infinity to plus infinity. So if you see a Fourier transform, जिसके अंदर सिर्फ एक frequency के ऊपर impulse पड़ा हुआ है, right? That must indicate that the time domain signal is just one complex exponential of a single frequency. A singular frequency उसमें मौजूद है, and that singular frequency in this case resides at omega equals omega naught. Okay, and so that makes perfect sense, intuitive sense, right? Now, what about cosine omega naught t? If I ask you to find the Fourier transform of cosine omega naught t, what would that be? How do I go about this? Okay, excellent. So Ibrahim says, why don't we use Euler's identity? So x of t is equal to half e raised to power j omega naught t plus half e raised to power minus j omega naught t, right? So now I can just deal with these separately and apply sort of a linearity of Fourier transform, which is what? X of j omega is defined as what? Is minus infinity to plus infinity, x of t e raised to minus j omega t dt. So therefore, this is equal to integral from minus infinity to plus infinity, half e raised to power j omega naught t plus half e raised to power minus j omega naught t times e raised to power minus j omega t times dt. And this is minus infinity half e raised to power j omega naught minus omega t dt plus half minus infinity plus infinity e raised to power j minus omega naught minus omega t dt. Now, what is this equal to? We found out what this is equal to, right? Excellent. Right, Ibrahim already has the answer. So what is this equal to? This is equal to, as we just did up above, this is equal to half delta omega minus omega naught times 2 pi. And this is equal to 2 pi divided by 2, and this turns out to be delta omega plus omega naught, right? And therefore, x of j omega equals pi delta omega minus omega naught plus pi delta omega plus omega naught. So this, the Fourier transform of a cosine is two impulses. So x of t equals cosine omega naught t has the following Fourier transform, j is kr. So x of j omega, there's an impulse residing at omega equals omega naught, which has a height pi, and there's an impulse residing at omega equals minus omega naught, and the height is pi, right? And there are two impulses, and that makes sense. Your cosine omega naught is made up of two exponentials. One has a frequency of plus omega naught, the other one has a frequency of minus omega naught. And if I look at the Fourier transform, I just see, yeah, there are only two singular frequencies present in this time domain signal, one of them at omega naught and the other one at minus omega naught, which makes perfect sense. Okay, so this is where I'm going to stop.
Excuse me, sir.
Ji then.
सर अगर मैं इसको रिवर्स इंप्लाई करूं कि अगर ये वाला ग्राफ मेरे पास टाइम डोमेन में और उसका फोरियर सीरीज निकालूंगा तो वो cos ओमेगा नॉट टी आएगा ना, लाइक जैसे हमने पहले वो किया है, चेक किया है।
यस,
ठीक है
बिल्कुल, एक्सीलेंट।
सर।
राइट, बट विद स्केलिंग, डिफरेंट स्केलिंग होगी उसके अंदर, लेकिन सिर्फ एक 2 का फैक्टर कहीं पे होगा, 2 पाई का फैक्टर आएगा एक्स्ट्रा।
जी सर, ठीक है।
All right, so I'm stopping here. I'll take any questions that you may have. जी इब्राहिम।
जी सर, मेरा एक क्वेश्चन था कि वो हम शुरू में हमने बात की थी कि पीरियोडिक सिग्नल्स जो होते हैं वो एब्सोल्युटली इंटेग्रेबल नहीं होते, तो वो आप एक दफा रिपीट कर देंगे, मुझे याद नहीं सही तरह आ रहा था किस तरह से।
कि एब्सोल्युटली इंटेग्रेबल क्यों नहीं होते?
जी,
उसके
क्योंकि
पास
पावर सिग्नल्स होते हैं इस वजह से।
हाँ, ये that's also a reason, but there's another intuitive explanation, right? So the periodic signals always goes on, right, from minus infinity to plus infinity, right?
जी
Or if you're integrating it,
जी, तो वो
right,
सारा ऐड कर रहे हैं।
सारा ऐड करें और सारी पॉजिटिव वैल्यूज ऐड करें, वो हमेशा डाइवर्ज करेगा।
जी हाँ, सही है सर, थैंक यू।
एब्सोल्युटली इंटेग्रेबल होने के लिए देखें, एब्सोल्युटली, सर प्लीज स्टॉप द रिकॉर्डिंग।